All right, so today we're going to go over the course logistics, and then just sort of have an overview of the course and the different aspects, and then we're gonna start actually diving in a little bit to what discrete event simulation is. Come on, why are you? Okay, so and apologies about the mix up about the times. I got this sort of panicked email from about trying to switch them because of some stuff that's going on in OR. So I'm not sure if that's going to be able to happen because my schedule, it turns out, is kind of oriented at this time. So that may or may not happen. But in terms of, so for the foreseeable future, we will meet at this time. Monday through Thursday lecture. Thursday is scheduled to be lab, but this week it's going to be a little different because as it turns out, I need to have one more lecture before the lab. So this week, there will be a lecture at 11 and the lab at 1. Why? Because I mean, I could throw you into the deep end without enough information, but I want to make sure that you're all prepared for that. So, and then sometimes with the labs, if there's something that I haven't quite gotten that would, then I might have, there might be a brief lecture at the beginning of that. Not, in those cases, it will be just some information that I think you need in order to make the lab go pretty well. We're not going to have any of those quizzes that I tortured you with last quarter, those in your room, so don't worry about that. But the labs are going to be mostly for your coding and my troubleshooting. So that now how that's going to work online, I'm not quite sure, but we'll see about that. Okay, in terms of the deliverables, in terms, there are going to be two types of assignments. There are going to be written assignments. Okay, this is going to be a little different for those of you who had the programming course. Those are going to be pencil and paper, or if you have a drawing program, that would, something like that would work as well. Those are going to be submitted electronically via Sakai. We didn't do that last time because we submitted your programs via GitLab. Now they're going to be computer assignments as well, and those you're going to submit using GitLab in a similar way as last time. And all this will be done with separate repository from last time called MV3302, big surprise. And just as last time, please, if you call it that, then that makes my life easy because I have a script that just goes and pulls them down and it assumes that that's what the name is. Now I have videos to refresh this. So even those of you who've done it before, you did it once 3 months ago. And if you're like me, then it may not be fresh in your mind. Videos to remind you of that. Now the textbook is a free download written by yours truly called Discrete Event Simulation Modeling. It's a PDF in the downloads folder. And what I'm going to do is where are you? Okay, so here's the Sakai site. This should look familiar for those of you who've had the programming class, for those of you who haven't. This is how it's organized. So the Zoom links are right here. For some reason, I had to create separate links for the 11 o'clock and the 1 o'clock because screen doesn't match. Okay. Oh. Oh, let's see here. Okay, can the remote people see this? Hopefully, okay. All right. So there are the Zoom. Now, those of you who are taking it in person, you're supposed to be here. If for whatever reason you can't, then you can come on via Zoom. So that's, and of course, as before, it'll all be recorded. Hopefully, this is still being recorded on Zoom. I hope I haven't messed that up. If not, then I'll have to do so. Anyway, so okay, the syllabus. Okay, the syllabus is here, and you all know how to read. So I'm not going to go through that. Here, important things, resources. Okay, there, the slides are going to be here. You can kind of peek ahead. I'll usually put a week ahead for there. Handouts, this is the main textbook here, so that you can download. And then the other thing is that for those of you who are using Java, then here's the SimKit library. There's a video about how to do all that. Now, the main organization of things is in the lessons link as before, and it's organized roughly by topics. So when you open this up, so they, now these are subject to change. So what I've done is I've pretty much put in the way I did it last time, but it may be a little bit different this time. And plus, as each of the classes occur, there'll be an the link will be upgraded. So there's that. Let me this as you would do it. Okay, so now there's already an assignment, and that's just to get the computer thing all set up. That's all actually right in here, and you pick your poison. So for those of you in person, you'll all be doing Java and SimKit. For those of you remote, you have a choice to do it in either Java or in Python. Just the caveat with Python is that the library for that is not quite as mature as that in SimKit. So results may vary. And that's pretty much it for that. I'm seeing some. Links below the Zoom links resources. Okay, well, thanks for pointing that out. I'll update those links. So now let's, any questions about the logistics of this? Now, one thing that is important to mention that okay, yeah, one the main takeaway from this class is actually not on the computer. The main takeaway is this discrete event methodology, and specifically something called event graph methodology that I'm going to get to a little bit later in this week. That is something that is separate from the code. It's analogous to those UML diagrams that we played with a little bit. So a UML diagram has nothing to do with code. In other words, you can write a UML diagram without writing a single line of code. What these event graphs are the discrete event simulation equivalent of that, where you can actually write an entire model on pencil and paper. And then what the programming part does, and that's what both of these libraries are set up to take one of these event graph models and just sort of translate it into code. So the programming is actually going to be a lot easier, and that's the easiest part of this whole thing, because that's just a matter of translating a model on a piece of paper into code. Just like if you have a UML diagram, you can sort of take that UML diagram and you can at least write what the instance variables are and what the instance methods are. There's no programming involved. You just kind of take what's in the UML and you put it into your code. So that's not programming. Now, in those cases, when you have to implement a method, then that's programming, because you have to figure out how to do it. The UML doesn't tell you how. Now, one of the differences is that the event graph will actually tell you how. That's the good news. The bad news is that coming up with these event graphs is hard. I mean, that not hard, but that's the most challenging part. The most challenging part is not going to be the programming. The most challenging part is going to be, from a description of a problem, can you write an event graph that will create a discrete event model of that thing? That's the most challenging thing. Why? Because that requires thinking, it requires creativity, and those things are both very difficult. Turning it into a program is easy. Comment here. Okay, so I'm having trouble seeing the chat on this, so apologies for that. And so if you have those remote, if you have a comment, you can unmute yourself and speak up.
I have a question about the assignments.
Yes.
Do we submit them, like the first assignment you just showed, it says that you cannot submit it online? Is that something, how do we let you know when we've completed that?
Great question. How do you let me know? You will let me know via your GitLab repository, which you will set up. And that's actually the first assignment is to set up that GitLab repository. And the final piece of that is to add me to that, which I didn't put in the videos, but I'll show you here how to do. Okay, does that, so the computer assignments will be done via GitLab, which you can do directly from your IDE. And the written assignments will be submitted electronically via Sakai.
Okay, thank you. And then I had one more question. Sure. It says the assignments due at 5 p.m. or is that Pacific time?
What time zone are you in? Remind me.
I'm in Pacific Standard Time.
Oh yeah, 5, and that's there just because that's kind of close of business day. I mean, that's yes.
Okay, and do we usually expect, because I'm used to it being like 11:59, for example, or midnight, so should we usually expect close of business to be the time that it's due for these assignments then?
In general, yeah.
Okay, got it.
And if that's a problem, I can push it off a couple hours if that would be more convenient. Okay. That's just to have a deadline on it. I mean, I'm not ultra strict about that in terms, as long, I mean, if it's a little bit late, that's kind of okay. With the thing is now with GitLab, because it's based on Git, there's going to be a timestamp for your stuff. So here's how that can impact things, because sometimes there might be network issues in terms of pushing it to GitLab, but if you've committed it locally, there'll be a timestamp on that. So for example, if you commit your computer assignment kind of before the deadline, but don't push it until after the deadline, then there's going to be a, I'll see the timestamp. So that'll all be okay. And again, just as a
Okay.
reminder, the way things are set up here, I can't see the chat. So, so again, if you have something, speak up. Oh, okay. All right, yeah, yeah, thanks. Okay, so now, just today I want to give an overview of what simulation modeling to kind of place what we're going to be doing in the context, well, especially in the context of moves, because moves is modeling virtual environments in simulation. This is obviously part of the S of moves, and there are many, many differences and different purposes of simulation. Most of the other, in the other classes, the simulation is oriented towards the use of training. What we're going to be doing here is more oriented towards analysis. That is, taking a situation and saying, okay, what is going to happen? What would happen if we did this? What would happen, you know, like in some of the models, my most recent models, which have to do with inventory policies for NABSUP, they're asking questions like, well, what should the policy be in terms of reordering things? What would happen if we change that? What would the impact be on things like fill rate, in terms of costs, in terms of back orders and other types of things? All that is analysis. Now in training, the purpose is very, very different. The second bifurcation, as it were, of different types of simulation models have to do with how time is modeled. And a simulation is a, you know, just broadly speaking, we're creating an imaginary realm. And in that realm, we have to control everything. Like when we are running it on the computer, everything in that has to be controlled by the modeler. Now, a big part of that is how do we model time? Now, you may be used to the most simple, most straightforward way, which is called time step. And you're going to hear a lot of complaints about that. Why is discrete event simulation called discrete event? What is so discrete about it? What is discrete about it are that the events are the main focus of things, and when the events occur are the main orientation. In other words, the time between events is not fixed. And so, as we'll see, what that allows us to do is to kind of accelerate time as events happen relatively sparsely, and slow down time when events happen very, very quickly. Whereas in a time step, what a time step does is it says, okay, well, we're gonna fix a certain time increment. We're gonna click the clock by that, say, a second, and then update everybody. Then take another second and then update everybody. Turns out that's, of all the ways to do time advance, that's the worst. And now, part of the problem is that people are kind of really, time step is the first thing, like when you first see simulation, time step is usually the way that it's presented. And so one of the problems is that there's kind of a duckling phenomenon going on here. In other words, if that's the thing that you've imprinted on, then that's the thing that you kind of grip tightly and have a hard time letting go of. So even some of my colleagues, not in this department, but kind of elsewhere, having, keep trying to say, well, we can put a Band-Aid on, we can fix up time step to overcome some of these problems. Turns out time step has some issues. What we will be doing is something called next event. And what next event is about is moving time until the next interesting thing. And you'll see some specifics about that. The other is one of my favorite quotes, and if you hang out in the OR department, you'll probably hear a bunch of this. But this is, I think, a very important thing to keep in mind, and that is all models are wrong. Okay. Now the corollary is that some models are useful, but all models are wrong, and there's still some confusion about that, because because every model is wrong, no matter how realistic you try to make it, it's still a model. And there's going to be big parts of the model that are going to be left out. In fact, most of what you're trying to model is not going to be in the model. And some people have a hard time wrapping their heads around that. So now that doesn't mean a model, now models can be useful, just you need to understand what it is that they leave out, and what they put in. What do you put in? Hopefully you put in everything which is impacting your results. If you leave something out that is impacting your results, then your model is going to be egregiously wrong. But if you've captured most of the characteristics of the thing you're modeling that impact what you're trying to find out about it, then it should be okay. So for example, like one of the first things we're going to look at are queuing models. Queuing is just sort of a fancy word for waiting in line. So let's say we're modeling. Back before ATMs, people used to actually kind of go into a bank and kind of do business there. And if we wanted to model it, typically when you go in, you have to kind of wait online. Or kind of something that still comes up, we're flying again, and when you go to the airport, whether you're trying to get onto one of the just self-check kiosks or one of the ticket counters or whatever it is, you're waiting in line. Now, if we want it, we can model that. We can model all sorts of things. There are lots of things about that situation that we're not going to model. Like, what color are the walls? Are there paintings on the walls? What kind of floor is there? We're probably not going to include that in the model, but that's part of the system we're trying to model. So it should be pretty intuitive that if we're trying to evaluate how long the lines are going to get or how long you're going to have to wait, that kind of what color the wall is probably isn't going to affect that, at least significantly. So, okay, so all models are wrong. We will be using a framework based on discrete event simulation, and there are 4 parts of a discrete event simulation model, only 3 of which I've listed here, but the states. So when we are creating a simulation model, we explicitly say these are the states. Events, those are the things which cause the states to change. And the mechanism by which that occurs is something called the event list. And what the event list is you can think it's basically a sorted set of all the events that we know about that are going to happen in the simulated future. So okay, so I'll talk about the structure of a model, and hopefully, well, see, I think I have time just for one example. So we define our model by a collection of these states. So that's kind of the first concept. So what is a state? A state is something which basically can kind of change. So one of our canonical examples is going to be waiting in line. Why? Because that it turns out to be a very challenging problem. So one state that we might have is how many people are waiting in line. Or think of maybe the food place in there. Like sometimes you go there and you can get served right away. Sometimes you go there and there's a line, right? So so a state of that would be how many people are waiting in line. Now, what makes discrete event simulation different from other types of simulations is that the state trajectories are piecewise constant. So I'll talk about what we'll see what a state trajectory is. The state transitions occur instantaneously in simulated time. In other words, let's say if we're waiting in line to get the food, if somebody joins, then all of a sudden the number of waiting in line is one more than it was an instant ago. And in the model, physically in reality, that happens in a certain finite amount of time, but in the model, it's going to happen instantaneously. These jumps are what we call events, and that's what allows this to be particularly, it allows discrete event to be more efficient. That was the original motivation, but it turns out that it also makes things kind of go more smoothly. Okay, so a state is a variable that describes a snapshot of the system. So if we are, no matter how complex the system, if we were going to stop it, then and then say, okay, what are the values of these states? That would provide a snapshot of the system at any point in time. So if we were, if we're modeling the line at the food place, if we were to kind of just take a snapshot, there would be a certain number of people waiting. That would be that number. And if we took a snapshot later on, there would be a different number. So a state trajectory, used that term in the previous slide, but what is a state trajectory? It's you can think of it as a graph of the state over time. Now, because the discrete event simulation states change instantaneously, well, the implication is that the state trajectories have to be piecewise constant. So what does that mean? That means that there are some state trajectories that are inadmissible. In other words, here are two of them, actually three of them. So this is time here. This is over time, and this is just what the value is. So here's a state that's increasing exponentially. Here's a state that goes as a parabola. Here's a state that just kind of wanders around. But because these are continuous, none of these three state trajectories can be represented in a discrete event simulation model. You say, well, that's terrible news. Well, guess what? None of these can be represented in a time step model either. In fact, none of these trajectories can be represented on the computer at all. Exactly. They can be approximated. Okay, but here is an admissible state trajectory. This piecewise constant. And so we haven't defined what this value is, but here's simulation time. And so this state starts off at this value. It keeps going at that, and then all of a sudden, in 0 time, it jumps up to a new value. It stays there for a while, and then jumps down to another new value. Stays there for another amount of time, jumps to this value, etc. So first of all, as you can see, the amount of time that the state stays in each possible state value varies, or at least it can vary. Now, the utility of this is that all of these, because these are discrete points on the line, these are what we identify as events. In other words, this is the event that the state goes from this value to this value. And this we can identify with the event that it goes from this top value down to this intermediate value. So the fact that these state trajectories are piecewise constant allows us to identify these key elements. And the way that the event list works on this is that you would start at time 0, and the very next thing that would happen is that we would actually advance time all the way to that next event. So we would jump over all of these things. And then in this case, the very next thing, it would advance time that much. Each of these are just one iteration. So the amount of simulation time that it advances depends on when the next event is. Now, that's a very simple situation. In general, we're going to have lots and lots of these states, and they're all happening at once. These events are just kind of pouring onto the event list, and the event list is sort of scrambling to take care of it. We'll kind of dive into what the event list is about. In fact, the first thing we're going to do, not today, but tomorrow, is actually be the event list. We're going to be the event list, and we're going to process these events as if we were. These events are the interesting occurrences. And what is interesting? The only interesting thing in general is a state transition. In other words, if a state doesn't change value, it's just going to be the same value. Between events, nothing happens in the model. And so there's really no point in, like, if you know that a state variable isn't going to change for a certain amount of time, there's no point keeping track of it. Well, what's your value now? What's your value now? What's your value? That kind of polling is the worst and most inefficient way of figuring it out. Now, when we start modeling, these events can schedule other events. So that's the other thing on top. So events consists of two pieces. One piece is the state transition. And when we're defining the model, when we're defining an event, we define what that state transition is. We'll see an example soon. And the second piece is it schedules other events. Now, the order that the events occur is not necessarily the same as the order that they're scheduled in. So, for example, in our model at the food court, there are basically kind of two things that affect the number of people in the queue. One is somebody kind of comes in, but the other is that one of the servers finishes serving somebody, and you can then move from the queue into getting service. So those are two different things, and they can happen whenever they happen. So the event list keeps the events in the right order. We'll see examples of that. And so when an event gets scheduled, we'll say, the next event is going to happen with a certain delay, a certain amount of time after when it actually happened. And the event list being a sorted set, like it's literally a sorted set in the implementation, it keeps them in order. So if an event is scheduled but happens after other events that are already scheduled, then it just gets put on the event list and then waits its turn. The event list processes things by advancing time to the next scheduled event. It removes that event from the list, but then it processes the event. What does that processing mean? It means it performs the state transition that's defined in that event, and it adds any scheduled events that particular event has been defined. And it keeps doing that until the event list is empty. And when the event list is empty, that means basically the universe is ended. So that's the end of the world as we know it. Okay, so now, if you're thinking of sorted sets, when you instantiate a sorted set, how many things are in it? Nothing, it's empty. So initially, the event list is empty. So we need at least one initial event. So the way that the methodology is set up is that every model defines one event. And for historical purposes, it's called run. Why is it called run? Because the guy who invented event graphs, which was not me, but somebody else, that's what he called it. So that's what I call it. So you can think of run as almost like it's sort of like the main method, so it's like, how does a Java program know where to start? Well, you say, use this main file, you start with main and then you start processing. Run is sort of similar. The difference is that we can have lots of different runs, as we'll see. But otherwise than that, it's processed like any other event. So given all that, what is the structure of a discrete event simulation model? Well, we've talked about states as variables, but there are also, it turns out that in order to to make it, to keep from going too crazy, it's very helpful to have parameters. So every discrete event simulation model has two types of variables. One of the state variables that we've talked about, and the other are parameters. So what's the difference? A parameter is something that doesn't change during a simulation run. And changes in quotes because as we'll see, sometimes a parameter could be a sequence of numbers, but that sequence isn't going to change. But a state variable typically does change. And I say typically because it is technically possible for a state to not change for a particular run, but that's only by chance. In other words, by chance, a state that could have changed somehow didn't change. Why? Because the events that caused it to change never happened in that particular execution. Okay, but those are the two variables, parameters and states. And then events are when the state transitions occur. And then the final piece are the scheduling relationships. Remember I said that events can schedule other events. So that's actually a binary relationship. In fact, it's a directed binary relationship, and that's the key behind modeling this as a graph. So, okay, so this is all a bunch of talk, but let's look at the hello world, or the simplest non-trivial discrete event model. And that's called the arrival process. So what we're modeling here, we're just sort of modeling things that kind of show up. And when do they show up? Well, that's our parameter. The parameter is, lost the mouse here, but okay, so the parameter is just some sequence of inter-arrival times. Those are the times between when they show up. And that's a parameter because those values are kind of exogenous to the model. They're kind of outside the model. When most of the time, we're going to implement those using a random variable, most of the time. But nevertheless, we can think of that. It's a parameter because that's kind of separate from the model. We can get those values without having to create the model. But our state is going to be the number of arrivals. My mouse disappear. Okay, you can see it here, but I can't see it here. Oh, this is crazy. All right, okay, so so there are two events. There's the run event. Okay, so there's the run event, and then there's the arrival event. So remember, we said that we always have to have a run event, and the run event, we'll get into this more as we go on. But the run event has two main responsibilities. One is that it initializes all state variables. So in this particular case, our state variable is the number of arrivals. We're simply going to count the number of arrivals. Now, when we start, how many arrivals have happened? None. And so the initial value of n is going to be 0. So the run event is responsible in general for assigning the initial value to all state variables. And then it's now the run event, this is the other thing, a run event, there must be at least one additional event that gets scheduled. Otherwise, see what's going to happen is the event list is going to put run on the event list to start with. So it starts off non-empty. And then it's going to execute that run event. If it doesn't schedule anything else, then the whole thing's just going to die right there. So what this run, in this case, this schedules our first arrival, and the delay is going to be that first inter-arrival time value. Okay, so that's what it does. And so that, in other words, that defines the model. That defines the event, the run event. And now what is an arrival event? So now the name arrival is totally arbitrary, just like the name of a method is an arbitrary label. So there's nothing about calling it arrival that makes it an arrival. What makes it an arrival is actually the state transition And what does it mean if something arrives? It means we have one more than we had before. And so if we're counting the number of arrivals, we're going to say that there's going to be one more arrival than there was before. In other words, the state variable n is going to increase by 1. And then now this arrival event is going to schedule the next arrival. So what's useful about this? Now, supposing we're in a model where we're going to have like 1 million arrivals. And they're going to come kind of one after the other like this. Now, what we could have done is we could have said, okay, we're going to put all of them on the event list at once. But that would be very wasteful, and it would be very inefficient, because now the event list has to deal with 1 million things on its list. Instead, since we know that they come one at a time, then at any given time, there's actually going to only be one event on the event list. And that's going to run pretty fast. In other words, we don't need to know what the second arrival event happens until the first one does. Okay. Now, here's the interesting thing. This is a simulation model in every sense of the word. You say, what is a model? This is a model. This is a discrete event simulation model in every sense of the word. And I haven't written a single line of code. So here's a possible state. Now, in this particular case, here's a possible state trajectory for this. Where now in this particular case, the state variable n, the number of arrivals, is only going to go up. It's never going to go down. So here's a possible state trajectory where it'll stay at 0 for a while till that first guy shows up. Then it's going to pop up here to 1, and then pop up to 2, and then pop up to 3, and then et cetera, et cetera. So the state trajectory for this model is going to be piecewise constant. So, but again, this is a simulation model in every sense of the word. And it's unlike a UML diagram. This is a complete model. In fact, this is going to be the first model that you'll ultimately implement, whether in Java or in Python. But the thing is that the design of the model is completely specified here. So the coding is going to be very, very straightforward. All you need to do is just learn what the just basically how to do it. Okay, so now this is covered in the first few sections of the discrete event simulation modeling thing. Now on the Sakai, there is a computer assignment 0. I wanted to get you started on that because there are always a few little glitches on that. And that involves kind of a couple of steps: setting up GitLab, setting up your IDE, and then for those of you using Java, getting SimKit on it. Again, that is in the videos. And for those using Python, I recommend PyCharm, but if you use a different one, contact me and we'll see if I can figure out how to do it. And then just sort of by the what I found in this is that I also have a kind of like MPD going on with this because I've gotten sort of whiplash going between Java and Python. This is my first time trying to do them both at once. So there's going to be some glitches on my part. And then for those of you who do use Python, just sort of know that I'm a Java programmer. And so I program Python with a Java accent. Just anyway, so okay, that is it for this. Hopefully, it has been recording. Okay, yeah. Now, any questions, concerns? Okay, that's it for today. I will see you same bad time tomorrow.